In section 7.7, I'm going to go over how to find a quadratic model in standard form for a set of data. And then we'll also discuss how to choose the appropriate kind of model for a set of data. Consider this set of data, which gives the domestic airline fuel prices for various different years. T is the number of years since 2000. We'd like to find a quadratic model for this data. Now, a quadratic model will be a model that's in the form y equals ax squared plus bx plus c. And the first thing I'm going to do is make a scatter plot for this set of data to see if it does appear that a quadratic model would be the best choice. So I'm going to put this data into my calculator and make a scatter plot. So we'll go to Stat and then Edit, and I'll put the x's into L1 and the y's into L2. So the x's are 0 through 8, because that's really the number of years after 2000. And then in L2 we'll enter in the fuel prices. Okay, now that I've got this data in, I just want to make sure my stat plot's turned on, so I'll do second y equals. And no, it's not on, so I'll hit enter on plot 1 and hit enter again to turn it on. And then just zoom, and then 9 will give me a scatter plot. And you can see that the data is kind of curved. It kind of looks like it comes down a little at the beginning and then goes back up. And whenever you have a set of data that does that, you know, it decreases and then increases, or vice versa. Maybe in another situation, something is increasing and then decreases. A quadratic model could be a good choice for that, because as you know, a quadratic function will be a parabola, and that has a vertex or a turning point in it. Now I'm going to use the method we learned in the last section to actually find a quadratic model for this. Remember in the last section we learned how to find a quadratic function that passes through 3 given ordered pairs. Now in this table we have a whole bunch of ordered pairs given to us because each row is an ordered pair. So all I have to do is choose 3 of these. And I'm going to choose the y-intercept for 1, because you might remember that when we use the y-intercept it makes it an easier problem to solve. So that would be 0, 80. That's the y-intercept. And I'm going to choose a point somewhere in the middle. I'll take this one, 4, 115. And then 1 toward the end. In fact, I'll choose the last point, 8, 310. And I'm going to find a quadratic function that passes through those 3 given points. Now on the graph, you can see those points are going to be right here. There's your y-intercept. And then 1, 2, 3, 4. That would be that point. And then this point. So I'm kind of spacing them out. I'm getting one at the beginning, one at the end, and one somewhere in the middle, thinking that if I find a parabola that passes through those 3 points, it'll fairly closely match the rest of the points as well. Okay, so I'm going to give myself some clear space because this will take a little work to find this quadratic model. So I've written down the 3 ordered pairs at the top here that I'm going to base it off of. And we are looking for an equation that's of the form y equals ax squared plus bx plus c. And remember, our procedure is to take each ordered pair one at a time and substitute the x coordinate in for the x and the y coordinate in for the y. So in this first order pair we plug a 0 in for x and an 80 in for y, and that would give us 80 equals a times 0 squared plus b times 0 plus c, and that simplifies down to just 80 equals c. Remember, when we use the y-intercept, that's a nice feature of that. We get c right away. Then if we move to the second point, we'll plug in 4 in for x and a 115 in for y. So 115 equals a times 4 squared plus b times 4 plus c. That one's going to simplify down into 115 equals 16a plus 4b plus c. And then for the last point, we'll substitute 8 in for x and 310 in for y. So we have 310 equals a times 8 squared plus b times 8 plus c. And that simplifies down to 310 equals 64a plus 8b plus c. Okay, now we'll actually take this. We know c is 80, so we'll plug that into in for c in both of those equations. And that will give us 115 equals 16a plus 4b plus 80. And in the second one, we'd have 310 equals 64a plus 8b plus 80. And then we want to subtract 80 from both sides from these equations. So if we subtract 80 from both sides in this first one, we're going to get 35 equals 16a plus 4b. And in the second one, if we subtract 80 from both sides, we get 230 equals 64a plus 8b. Okay, now we have right here a two-dimensional system of equations. There's two variables and two equations. So we want to get either the a's or the b's to be opposites and then add the equations together. And I'm going to get the b's to be opposites because 8 is 2 times 4. So if I multiply the top equation by -2 and then add it to the second one, that'll make the b's cancel out. So I'm going to multiply the top equation by -2, and that would give me -70 equals -32a minus 8b. And then I'm going to add that to the bottom equation. And when I do that, the b's are going to cancel. And we're going to get 160 equals 32a. And then when we divide both sides by 32, a equals 5. Now that we know a, we can substitute that answer into either one of these two equations, and we can find b. So if I take it and plug it into the top equation, we'd have 35 equals 16 times 5 plus 4b. So 35 equals 80 plus 4b. If we subtract 80 from both sides, we get -45 equals 4b. And then we'll divide both sides by 4. So -45 divided by 4 comes out to be -11.25. And sometimes we're going to get decimal answers when we're doing an application like this. So if we take our a, our b, and our c, and we substitute it into our equation here, we end up with y equals 5x squared minus 11.25x plus 80. And that would be our quadratic model. Now in our case, we would use a t instead of an x, so we could write that as y equals 5t squared minus 11.25t plus 80, because t represents time in years. But that would be our quadratic model for this set of data. Now to check to make sure that's right, I'm going to go back to my calculator and pull up that scatter plot and add this equation in and make sure it does pass through the 3 points I chose at the beginning. So here's the scatter plot that we did before, and what I'm going to do now is just press y equals and enter our equation in. So 5x squared minus 11.25x plus 80. And then just hit the graph key. And that adds that graph in there. And you see, to check this, it should pass through the 3 points that we chose at the beginning, which was this first one, the y-intercept. And then we chose that one, which corresponded to t equals 4. And then this last one, where t equals 8. And you see the curve does pass through those 3 points. And it comes reasonably close to the other points in the scattergram as well. So it seems to be a pretty good model for that set of data. Now, another option for finding a quadratic model for a set of data is to use our graphing calculator to get a regression equation. Now, regression is a statistical procedure that uses all the different points in the scattergram to find a curve that most closely fits the points. And we can kind of pick different kinds of regression. We can pick linear regression if the data appears to be in a straight line, or we can use a quadratic regression like we would in this example, where it tends to change from decreasing to increasing. Or there's even something called an exponential regression that I'll look at in a minute too. But I want to focus right now on a quadratic regression. Now, the first step in doing a quadratic regression would be to enter all of your data into your graphing calculator, putting the x values in L1 and the y values in L2. And we've already done that. So now we want to use our calculator to get a quadratic regression for this scatter plot. So to do that, we will press the stat key, and then we'll go over to calculations in the middle, and then we'll scroll down to the one that says quad regression and hit enter on that. And then as long as the x's are in L1 and the y's are in L2, we can just hit enter again. And that gives us the result. And you can see we're getting an equation in the form y equals ax squared plus bx plus c, and it gives us the a, b, and the c underneath. So we can combine that into one equation by just plugging the a, b, and c in. And so we would get y equals 4. I'm going to round these off just a little bit. 4.62 t squared minus 9.59 t plus 78.87. Now, when you compare this model with the one we did when we chose 3 ordered pairs, it's kind of similar. For this first number, we got a 5, and this is 4.62, which isn't far off. We got a negative 11.25 for this middle number, and calculator gets negative 9.59. And we had a plus 80 at the end, and here it's plus 78.87. So the numbers are a little different, but reasonably close to the model that we found when we did it by hand. Now I'm going to graph this regression model through the scatter plot just to see how well it fits the data. So go ahead and press y equals, and we'll put our equation in. So 4.62 x squared minus 9.59 x plus 78.87. And then we'll just hit the graph key, and it'll graph that along with the scatter plot. And you can see that that model does fit the data points very well. Now I'd like to talk about the different types of models that are available and how to choose the right one in a given situation. There's 3 main types of models I'd like to go over today. The first is a linear model. And a linear model will work well if the data points follow a straight line pretty well. So as long as your scattergram has points that are generally following a straight line, of course they're going to be scattered around a little bit, but if you can kind of visualize a straight line passing through the points reasonably well, then it could be a linear model. And that line might slant up or down depending on the situation, but in either case, a linear model could be a good way to go. A quadratic model is going to work well when the points change from increasing to decreasing, especially. And sometimes it'll even work well when that's not true, but as long as there's some kind of a curve to the data points. So there's going to be some kind of curve, okay? And possibly it might even change from increasing to decreasing, like that. And it could go the other way around. Maybe they're going down first, and then they kind of reach a low point, and maybe they start up, like that. Because a quadratic model is the only one out of these three that's going to allow it to actually change from increasing to decreasing. So if you want a model that's actually going up and then comes back down, or it's going down and then back up, a quadratic model is your only choice for that. But it can work well even when that's not true, as long as there's some curve to the data. And then an exponential model, you want to use that when there's some definite curve to the points. Maybe they're curving upward, like this. An exponential model could work well for that. Okay, or maybe curving downward in this type of way, where it's kind of leveling out as it goes along. Okay, so an exponential model you want to use when the points are curved, but it doesn't change from increasing to decreasing. So it's either always increasing, like in this case, or always decreasing. And in these bottom pictures, you might even find that a quadratic model could work well there as well. And the way, even though it's not changing from increasing to decreasing, this could be a portion of a parabola. You can kind of consider that, that could continue around. So to figure out in these situations in the bottom here, which one would be better, you'd actually want to probably try both and see what fits better. But just to summarize, a linear, you're looking for a straight line pattern. That one's pretty simple. If your function actually changes from increasing to decreasing or vice versa, then you have to go with a quadratic model because there's no other way to model that. And then if you have a curvature in the points, but not so much that it's going to change from increasing to decreasing, then you could consider an exponential model or possibly a quadratic. You'd have to actually try both to see what fits better. So let's look at an example. Okay, so in this example, it gives the percentages of teenagers who smoked cigarettes in the past month for various different ages, 12 through 17. And, the first thing you'd want to do is just look at the values in the table. As the age goes up from 12 to 17, the percent seems to get higher every time. So we know it's an increasing function. So I've put these into my calculator. I put the ages in for L1 and the percentages in L2. The first step would be just to get a scatter plot of this, because that'll really start to tell us what we should be looking for as far as choosing what kind of a model between either linear, quadratic, or exponential. So let's go ahead and I'll press zoom 9 on this. Just let me make sure my stat plot's on, and it is. So then zoom 9 will give me a picture of this. And you can see the points follow pretty well along a straight line here. So it looks like it could be linear, although there is a little bit of curve, especially at the beginning here. I'm going to start by doing a linear regression. So that's this one right here, linear regression, AX plus B. And I'm going to store that answer into Y1. So if I press this vars key right here, and then choose yvars, and then function, and then y1, it'll not only calculate the linear regression equation, but it'll automatically store it into y1. And so here's the answer, and if I press y equals, you see that's put that into y1 automatically. So if I just hit the graph key, it'll graph that right along with the scatter plot. And you can see that fits it pretty well. Now I'd like to try the exponential regression to see if that's any better. So we'll do stat and then calculate. And we have to scroll down a little for the exponential regression. It's called EXP REG, this one, exponential regression. And so we hit that. And again, I'm going to store this into Y2 this time, because I already put the linear one into L1, so I'll choose Y2. And that just automatically stores the answer, so I don't have to retype it in. And you see this one's of the form a times b to the x power, and here's your a and your b. And if we press y equals, we'll see that that's put that into the calculator. And I'm going to hit graph, so it'll graph both models so we can compare. Now the exponential model, as you can see, curves, and it might fit a little bit better at the very beginning, but you can see it's getting pretty far off track here. It's going to kind of head off much too steeply at the other end. So I would say the linear model would be the better choice here, just because it seems to follow the data points more closely, especially at this right-hand side of the scatter plot. So I'm going to say that the linear model is best for this particular case. And the equation for that was y equals 5.12x minus 61.9. And I've rounded those values off a little bit. Okay, so that would be a pretty good model for this set of data. The exponential model, as I said, just doesn't seem to fit too well. It's too low in the center. It's going to be way too high on the right side as we project out into the future. Now in this next example, the table gives the amount of digital data stored on devices in a typical U.S. household measured in terabytes. And you can see we have data for the years between 2004 up through 2008, and the amount of data keeps getting higher. Not only does it keep getting higher, it gets higher by bigger and bigger amounts every year, which tends to tell you that it's not going to be a straight line. So I've entered this data into my calculator. I put the x values. These are the number of years since the year 2000. So 2004 became a 4, and then it goes up through 2008. And then these are the terabytes in L2. So you want to start just by making a scatter plot of this data. So we're going to just press zoom 9, and that'll give us a scatter plot of that data. Now you can see here that the points do tend to be curved somewhat. I mean, you could do a linear regression, but I wouldn't recommend it here because there does seem to be some definite curvature to these points. So I would try either a quadratic regression or an exponential regression. I'm going to start with a quadratic regression model. So I'm going to go ahead and press the Stat key, and then go over to Calculations, and then go down here to Quadratic Regression, hit Enter. And I'm going to go ahead and hit this Vars key here, and then yVars, and then Function, and then y1. And that'll just automatically enter this equation into y1. So here's the answers, and then you can see it is in y1. And so if I press the graph key, it'll show me how well that model fits the data points. And it, as you can see, it does tend to fit very good. So that appears to be a good model. So I wrote the equation of this model down right here. Okay, I've rounded the decimals off to 3 decimal places, and that gives us a pretty good model, and that's a parabola that's passing through those points as closely as possible. Now we also talked about the fact that the exponential regression might also do a good job at modeling this kind of a data where there's an upward curvature like that. So let's now try to do an exponential model. Now an exponential regression model is going to be of the form some number a times some other number b raised to the x power. So notice in this kind of a model the variable x is in the exponent position. Now I'm going to now use my calculator to find that exponential regression model. So we're going to go to stat and then calculate again, and then we're going to scroll all the way down to EXPREG, and then I'm going to go ahead and enter that automatically into Y2 like I've done with the other ones. And when we hit enter on that, we get our results. So you can see that's already been entered into Y2 automatically, and so I'm going to graph that. And that's the quadratic one, and now if you look carefully you can see another one being plotted in there. That's the exponential one. And the two models are almost identical here. Now I'm going to write the equation down for that exponential model. It was y equals 0.053 was the a, and I've rounded that off. And that's times b was 1.62 approximately. So 1.62 to the x power. And I'm going to use t instead of x because it represents time in years. So that would be our exponential model. Y equals 0.053 times 1.62 raised to the t power. So both of the models appear to fit the data points very well. As you can see from this graph, the two models are pretty much right on top of each other. So the question is, which one is better? Well, I would probably choose the exponential model as the better choice here, and I'll explain why. Okay, because if you're using a quadratic model, so this first one here, the graph is going to be a parabola, because we know any quadratic function is a parabola. So that means if we're assuming that this is a quadratic model, it's going to be a parabola, so it's going to come down, it's eventually going to reach a low point and come back up. So if we were to try to predict answers before this first year, 2004 is the first year in the chart, but if we were to try to go back in time, the model is going to tell us that households used more data on digital devices in years before 2004. And I don't really think that's true, because I think that's probably, you know, back before people stored a lot of stuff on digital devices. So because of that, I don't think a quadratic model would do a very good job at projecting or predicting values before 2004. Whereas the exponential model, on the other hand, we'll draw that one in green. Okay, what that's going to do, it's going to come down and it's just going to kind of level off like that, which I think would be more realistic. If we were to try to predict an answer back in 2003 or 2002, it's not going to go back up. It's going to probably continue down slightly. So for that reason, I think an exponential model is probably the better choice. Although over that time span from 2004 to 2008, both models do a very good job. So I hope those examples give you some idea about how to choose the best type of model between linear, quadratic, or exponential in a given situation.